Hello, I'm Chungyo In on the PhD course in the Industrial Management Engineering, Hanbad National University. Presentation topic is a study of drowsiness and awakeness using a non-contact radar sensor. Then I will start the presentation now. The table of contents is as follows. First, we will present in order of introduction, experiment, result, and discussion. According to the Korea Highway Corporation, 1,079 people were killed in the traffic accident on highway between 2015 and 2019. Among them, 729 people died from drowsiness. In other words, 6 to 7 out of 10 highway traffic fatalities appear to be accidents caused by drowsy driving. Let's take a look at the existing method for the drowsy driving. First of all, this is how to figure out drowsy driving based on face recognition. Check the driver in real time through the camera installed around the instrument panel or rear view mirror. Using a face recognition program, analyze eye shape and muscle change to determine if the driver is dozing off. Analyze the angle of the line of sight and the operation of the driver from various angles. Importantly, accumulate database are the core of technology. This is because the analysis is easy, but the criteria for judgment must be established. Additionally, 5G technology that can utilize fast real-time database must be accompanied. Recently, Hyundai Mobis recognized the driver face using infrared cameras installed inside the vehicle and identifies careless operation due to drowsy driving, distraction of attention, and accumulation of fatigue. It is also developing a system to prevent accident by calling drivers' attention to cluster marking, alarm sounds, and vibration by judging the risk of rain departure and rain intrusion due to driver carelessness. Technology to prevent drivers from the drowsy driving emerges into industry around 2010. However, there is a limit to applying it to mass-produced cars. Why is introduction of technology that have such a significant impact on the safe slow? First of all, it is possible to point out the limitation of communication infrastructure. Fast communication speed is essential to utilize vast amount of data in real time. However, communication speed varies greatly by country and region. And LTE technology is a limitation to utilizing a big data. There are also many restrictions because the driver's face cannot be recognized accurately when facing tunnels or driving at night, and face cannot be recognized when wearing sunglasses. The following is the method for detecting drowsiness using EEG. EEG often used to measure biometric signals. It detects EEG following around its head through a headset-type sensor and measures the driver condition in real time. The method of using EEG in drowsy driving can be used in the type of analyzing the information from the EEG to determine the driver's condition, and linking with the smartphone app to immediately send a warning when the driver's attention drops. EEG is largely divided into 5 types, and each EEG has its own characteristic and frequency value. EEG usually appears in order of delta wave, a theta wave, alpha wave, a theta wave, and gamma wave in order to low frequency to high frequency region. It can be interpreted as an arithmetic sum. At this time, it can be meaningful by identifying which type of EEG appear with more weight than other types of EEG. So if you look at the 3 brain researchers here, Cooper studied the relative power spectrum of each EEG through fast Fourier transform analysis for processing EEG data as an interpretation method of EEG signals. Coughlin and Eckstead told truck drivers that theta wave and alpha wave increase in the center of the brain as the driver become tired or sleepy after driving truck for a long time. Carbon suggests that the alpha wave increase when driving without tension, and that theta wave increase when driving under stress. Analysis of drowsiness using EEG also has several limitations, which are inconvenient because drivers have to wear brainwave measuring device on their heads. And it is difficult to measure in a natural state due to the burden of artificial measurement. Next, we'll look at the analysis of drowsiness using radar technology presented in this paper. Radar is a radio device that emits radio waves and use the reflect waves to check the presence of target, distance from the target, status, etc. By using the strength of radar, it is possible to detect various information from a distance that cannot be confirmed by human eyes or sense. Because of its geographical and locational distance, and it is possible to respond by checking the result. In order to implement radar functions that detect various information, broadband frequency utilization, which can be contain a lot of information and transmission and reception signals of repeated first and required. Radar sensing technology using impulse of ultra-wide band frequency characteristic is bringing rapid technological development as digital signal processing and RF technology advanced. Therefore, the scope of radar technology is also expanding to various fields such as healthcare, defense, and living safety. This paper aims to detect drowsiness by extracting respiration and heart rate data by combining the Doppler radar technology among radar technology with the non-contact biosignal sensor. This is the Doppler radar sensor module used in this test. We propose a gigahertz Doppler radar sensor system that can be measured remote biological signals only with a simple hardware configuration. The proposed radar sensor system includes a commercial chipset and flat type of manual device, considering characteristics of radar wave attenuation in the body according to the operating frequency characteristics. RF front-end module were developed using antenna, etc., and high sensitivity signal processing algorithms were applied to obtain biosignal information in time domain. The biosignal acquired through the radar displayed by calculating respiration and heart rate through the signal processing. This sensor acquires data by detecting minute movement of the human body, such as heartbeat. The accuracy of this measurement varied depending on the distance, but in general, it was measured within 1.5 and 3 meters. Since the accuracy of the radar sensor is very important in this test, proper frequency setting and noise can be removed is required. Therefore, the frequency was set to 24 gigahertz in the most optimized section, and a filter for ambient noise was also developed to minimize noise. The signal collected from the radar sensor for a certain period of time is usually displayed in a form of a frequency through the fast Fourier transform. And the known heart rate is 50 to 90 beats per minute, and the respiration rate is 12 to 48 beats per minute. By converting this to frequency band, heart rate appears in the frequency band between 0.8 and 1.5 hertz, and respiration occurs in a frequency band between 0.2 and 0.8 hertz. This conventional method shows an accurate peak as the number of data having periodicity increased due to characteristic of fast Fourier transform. However, since the human heart rate contains a human body specificity and does not have complete periodicity, depend on the characteristics and conditions. There is a limitation in respiration, it as a single peak there is. Since the acquisition of biosignal variation information, that variety with the time is an indicator according to the activation of the sympathetic, parasympathetic nervous system, and contain more human body information than the heart rate per minute. In order to use the signal acquired from the radar sensor at the same levels as the ECG, the radar sensor, it is necessary to process the output in the time domain to obtain biosignal characteristics. Next, the experiment was conducted on the subject. 10 healthy men and women in their 20s who had never had any heart disease voluntarily participate in the experiment. The average height of the subject was 168.97 centimeters. The weight was 80.82 kilograms, and the BMI was 28.66 kilograms. Subjects were instructed to refrain from consuming caffeine, drinking alcohol, smoking, etc. that could affect the ECG measurement on the day of the experiment and to get more than 7 hours of sleep. In this test, the temperature was 27 plus minus 3 Celsius. The humidity was 57 plus minus 2%. And the illuminance was 21 plus minus 3 lux. A Doppler radar sensor was placed on the desk and the electrocardiogram and respiration rate were measured for 10 minutes. At the same time, biosignals were measured with a BioFAC device. After measuring the awakening state signal for 10 minutes, an eye patch and earplug were applied for 20 minutes. And then the subject were placed in a sleepy state by lying in bed. After 20 minutes, he got up immediately and measured the electrocardiogram and respiration rate in the same method as in the awakening state. At the same time, biosignals were measured with a BioFAC device. The electrode position during the ECG measurement using a BioFAC is shown in the figure below. The negative electrode was attached to the right chest, the positive electrode to the left abdomen, and the ground electrode was attached to the left chest. The sampling rate of both the Doppler radar sensor and the BioFAC MP150 was set to 200 Hz. As shown table 1, the average of the MP150 is higher than that of Doppler's radar sensor, and the heart rate, HRV, and respiration measurement result of the Doppler radar sensor and the MP150. Standard deviation was smaller in SD of a Doppler radar sensor. As a result of t-test, the difference between the two devices was recognized at the significance level of 1 point as shown in table 2. The following graphs show the significance level of the result between the radar and the MP150. As a result of observing the HRV change of the Doppler radar sensor and MP150 during the awakening and drowsiness, both devices shown a tendency to decrease HRV during a drowsiness as shown in table 3. In fact, as a result of the t-test as shown in table 4, HRV was decreased during drowsiness compared to awakening, and a statistical difference was recognized at the significance level of 1%. The result of comparing the radar and the MP150 both show a decrease in HRV in the state of drowsiness. Now, let's summarize what we have presented so far. Various studies have been conducted so far to detect drowsy driving, including facial recognition, EEG analysis, and radar method. But some point out that it is a technology of a transitional nature. If self-driving technology improve in future, drivers' condition does not affect safety. Therefore, the driver's concept itself disappeared. The instruction of lane maintenance assistance and emergency automatic braking system, which are part of autonomous driving technology, is also helping to prevent accidents. Eventually, it cannot ignore the cost of reducing duplicate investments by introduction a new level of technology. In this study, we were able to apply a radar technology to analyze biological signals in a non-contact method and check the drowsiness. In particular, this study sought to measure and compare ECG parameters, heart rate, HRV, respiration, with existing ECG measurement equipment and non-contact radar sensors. Therefore, there are two main methods of comparison, one between equipment MP150 and Doppler radar, and the other during awakening and drowsing. First, the mean value of MP150 was higher than that of Doppler radar sensor in all parameters. But the deviation of the Doppler sensor was small and the variability was low. For comparison of awakening and drowsy status, both equipment had reduced HRV in drowsy status compared to awake status. This result means that change in a biological signal occur when drowsy. And in reverse, they can detect sleepiness through change in a biological signals. In future study, it is expected that research on a medical field and remote monitoring utilization will be needed by increased Doppler radar antenna and frequency range to analyze the accuracy of the resulting data and correlate it with measurement distance. This is end of presentation. Thank you.